Today we're going to talk about logarithmic equations. Logarithmic equations. Okay, so first of all, I should start by telling you what a logarithmic equation is. So here's a definition. A logarithmic equation is one where the variable is stuck inside a logarithm. It's important to sort of be able to identify what kind of equation you have in front of you. As you learn how to solve more and more kinds of equations, identification of the equation type becomes more important. If you know how to solve like 10 different kinds of equations, linear, quadratic, logarithmic, exponential, all this stuff, you know, in order to know which procedure to implement, you've got to be able to identify the kind of equation that you have. So don't underestimate the importance of knowing this definition. A logarithmic equation is one where the variable is stuck inside of a logarithm, okay? All right, so obviously I'm going to tell you how to solve logarithmic equations, but before I do that, I need to actually give another definition. So I'm going to define a new operation. The operation is called exponentiation. This is a new operation that you can do to both sides of an equation. You already know that obviously you can divide both sides of an equation by a number, or you can multiply both sides of an equation by a number. You can add a number to both sides. There's all these things you can do to both sides of an equation, and this operation, which you probably haven't seen before, is just another operation that you can do to both sides of an equation. So let me tell you what exponentiation is. So let's suppose that we have some equation like, I don't know, 2x is equal to 7, okay? Obviously that's an equation we know how to solve. I'm not interested in solving this equation right now. I actually just want to show you what this new operation is. So if I exponentiate, that's the verb, exponentiate both sides by 5. What does that mean? Here's what it means to exponentiate both sides of this equation by 5. It means both sides of this equation become an exponent of 5. So the entire left-hand side becomes an exponent of 5. And the entire right-hand side becomes an exponent of 5. That's what it means to exponentiate by 5. Now, of course, you can exponentiate by whatever you want, right? Just one more example, maybe. Let's say you've got the equation x plus 3 equals 2x plus 1. And let's say we want to exponentiate by, I don't know, 6, okay? So what does that mean? It means that both sides of this equation become an exponent of 6. So if I exponentiate by 6, I get, you know, this whole left-hand side becomes an exponent of 6, and the whole right-hand side becomes an exponent of 6. So that's this operation, exponentiation. This is the operation that you use to solve logarithmic equations, okay? All right, so I'm going to give you some steps for solving logarithmic equations. Exponentiation is the most important step, but there are sort of some other things that we have to consider as well, and I'll just sort of make those clear with the following steps. So here are the steps for solving logarithmic equations, as I see it. So step 1 is the following. I would say step 1 is that you should use log rules to condense any logarithms. So if you remember the lesson from last time, we developed, or I showed you these log rules, and I showed you how to use those log rules to condense multiple logarithms together. In some logarithmic equations, you will have multiple logarithms, like on one side of the equation, And what I'm telling you to do here is, if that happens, if you have multiple logarithms on one side of the equation, then you should use log rules to condense those logarithms into a single logarithm. Lots of the time, much of the time, you only have one log of the equation, and this step isn't even necessary. But, if necessary, you should do this. Step 2 is, this is the most important bit, you should exponentiate. Okay, that's this operation that I defined above. You should exponentiate both sides, right? Now, if I tell you to exponentiate, I have to tell you to exponentiate by, well, by what, right? I mean, here we exponentiated by 5, here we exponentiated by 6. So I'm telling you to exponentiate both sides of the equation. Well, exponentiate both sides by what? The answer is by the base of the logarithm. Okay? So if you have a log base 7 in your equation, then you should exponentiate by 7. Okay, and then basically step 3 is simplify. If you have done this correctly, then the logs should disappear. So if you've done all of this right, then the logs should just disappear, which is good. And then I'll just say step 4 is solve. After step 3, after you simplify things, the equation that you're looking at should no longer be a logarithmic equation. The variable should no longer be stuck inside of an exponent. It should be like a linear equation or something like that is more easily solved. Okay, so all of that's pretty abstract. Obviously, we need to do some examples. So I'm going to do a few examples. So here's example 1. Let's consider the equation log base 3 of x minus 4 plus 3 is equal to 5. Now, first of all, we should be clear, why is this a logarithmic equation? Well, because the variable is stuck inside of a logarithm. That's why it's a logarithmic equation. Okay. All right, so let's just follow the steps. Step 1 was to, if necessary, use log rules to condense the logarithms. I only see one logarithm here, so that doesn't really apply in this situation. There's nothing to condense. Now, the next step is to exponentiate both sides of the equation by the base of the logarithm. In this case, that would be 3, right? But I think that it is advantageous to isolate the logarithm here by itself before you exponentiate. It's not necessary, but it makes things a lot easier. So I'm going to isolate this logarithm by subtracting 3 from both sides. Okay? All right, so now the log is by itself. So now I'm going to exponentiate by the base of the logarithm. The base is 3, so I'm going to exponentiate by 3. And what that means is that both sides of the equation become an exponent of 3. So I have 3 to the entire left-hand side. The whole left-hand side becomes an exponent of 3. Okay? And same thing on the right-hand side. The entire right-hand side becomes an exponent of 3. All right, now, you're probably wondering, why would you do this? The equation just looks worse. The thing is, this expression here will actually simplify by quite a lot. This is very similar to those problems that we did yesterday. Remember where the logarithm was inside the exponent? Remember how the logarithm just kind of disappeared and you were left with whatever was inside the logarithm? That's what's going to happen. If you like, exponentiation by 3 and logarithm base 3 are inverse operations. They're actually just going to cancel out, and you're going to be left with just the thing that's inside the logarithm, which is just x minus 4. And the right-hand side is just a number. It's 3 squared, which is 9. Okay, and now I can add 4 to... So this is no longer a logarithmic equation. As you can see, the logarithm disappeared, so I'm going to add 4 to both sides and get 13. That's my solution. Just one quick, statement on this thing in the box here. If you're still having trouble seeing why this expression reduces to x minus 4, let's just run through the argument once again. Forget about this 3 right here for just a second, so just hide it. And look at the logarithm. It's log base 3 of x minus 4. What does that mean? It means the power of 3 that gives you x minus 4. Well, what are we doing with that power? We're raising 3 to it. By definition, you get x minus 4. Okay, so that's just a rehash of the kind of argument that I made yesterday. Okay, cool. All right, so let's do another example. This one a little trickier. So here's example 2. This time I'm going to use some natural logs. Let's just recall before I write the equation that if you have natural log of, say, x, what that really means is log base e of x, e being that special constant. Okay, so let's write down the equation. Here's my equation that I would like to solve. It's natural log of x plus 5 plus 3 times the natural log of 2 is equal to 3. All right, so what I want you to notice in this equation is, number one, it is a logarithmic equation. Why? Because the variable is stuck inside of a logarithm. All right, now what's the first move? Well, we should, if necessary, condense logarithms. In this case, we actually do have multiple logarithms, so what I recommend is that you condense these logarithms together into a single logarithm before exponentiating. So we have to condense these logarithms together. You might remember from yesterday when condensing expressions like this, there's kind of two things you could do. You could try to, you've got one logarithm plus another logarithm. Maybe you think you can just smash those together right away. You actually can't. You have to put the 3 on the inside first before combining them. Sort of an order of operations thing, like multiplication comes before addition, and the 3 is a multiplication thing, and the plus is plus. So the 3 should go on the inside before we try to smash these logs together. So I'm not changing that first term, plus, and then we have natural log of, now remember the rule says that if you have an outside multiplier on a logarithm, then the 3 goes on the inside, but it becomes an exponent when you do so. So it's like 2 to the third, right? And all of that equals 3. Okay, so let me just make one quick change here. I'm not changing anything. I just want to observe that 2 to the third is 8. Okay, so 2 to the third is 8. I feel kind of stupid writing a whole new line just for that one change, but whatever. Okay, so now we've got two logarithms being added together, and we can use that other log rule, which says, if you're adding two logarithms together, you can rewrite them as a single logarithm. You just have to multiply the two insides of the original guys. So these two logs are going to combine into a single log, and what's the interior going to be? It's going to be the product of these two guys here, so 8 times x plus 5. Bear in mind, 8 needs to multiply the entire inside of this logarithm. In other words, the 8 needs to multiply both the x and the 5, so it's going to be 8x plus 40, okay, equals 3. All right, cool. So now that we have condensed all of this into a single logarithm, we are ready to exponentiate. Now, exponentiate by what? Well, by the base of the logarithm. This is the natural logarithm. What is the base of the natural logarithm? Well, as I reminded you a moment ago, the base of the natural logarithm is this funny number e. So we are going to exponentiate both sides by e. So the entire left-hand side becomes an exponent of e, and the entire right-hand side becomes an exponent of e. Okay? Now, on the left-hand side, this expression here, just like the one earlier, is going to cancel, or it's going to simplify, I should say. The only thing that's going to be left is this expression inside the logarithm, the 8x plus 40. So that whole left-hand side just becomes 8x plus 40, and that equals e to the third. Really quickly, as far as why this thing simplifies down to this, I've sort of made the argument multiple times at this point. You can sort of say to yourself, all right, forget about the e for a moment. What does that natural log thing mean? It's the power of e, which gives you 8x plus 40. What are we doing with that power? We're raising e to it, so by definition, we get 8x plus 40. Or you could say to yourself, taking the logarithm and taking the natural logarithm, that is the logarithm base e, And exponentiating by e are inverse operations. Exponentiation and taking logarithms are inverse operations. They cancel each other out. That's why we do this. Okay, so anyway, this equation, even though it's got this funny e to the third symbol, it is actually just a linear equation. I mean, you know, we can solve it for x. So subtract 40, so e to the third minus 40, and then divide both sides by 8. So I have x is equal to e to the third minus 40 over 8, and yeah, maybe that could be cleaned up a little bit by distributing the 8 or something, but whatever, it's good enough. Okay. All right, so cool. Let's do, oh, my lights just went off. Let me see if I can get them to turn back on. There we go. It's my motion sensor lights. They go off if I'm not moving enough. I guess I'll try to move more. All right, so here's one more example. Let's consider something like this. So this is example 3. Let's say 2 log of x minus log of 3 is equal to 3 log of 2 plus 3. All right. So, like, first of all, what kind of equation is this? It's a logarithmic equation. Why? Because the variable is stuck inside of a logarithm. All right, so what's the first step for solving a logarithmic equation? Well, you should begin by condensing the logarithms. These two logs here are on one side of the equation. We can probably, like, smash them together. But remember, you should put this 2 on the inside here before you try to smash these together. So that's what I'm going to do. So I have log of, and remember the 2 becomes an exponent when you put it on the inside, so x squared minus log of 3 equals, and I might as well do the same thing over here, like this 3 can be put on the inside here, and it becomes an exponent, so log of 2 to the third plus 3. Okay, so now what do we have? Well, we've got one logarithm minus another. And remember that there's that logarithm rule which says that if you have one log minus another, then you can rewrite that as a single logarithm. You just have to divide the 2 insides. So it's going to be logarithm of this thing divided by that thing. So x squared over 3 equals, over here the only thing I'm going to do is replace 2 to the third with 8. So that's log of 8 plus 3. Okay. There's no way to combine these two things. That's a log, and that's not. Like, you're just stuck with 2 different terms over here, okay? There is a way, if you wanted, to bring this logarithm over to the other side and, like, dump the 8 into here so that you only have a single logarithm in the entire equation. In fact, I think I'm going to do that. But I'd like to also, I'm going to show you how to solve this thing in 2 different ways, because I think both are sort of important to know. So it's really nice when you have just a single logarithm in the entire equation. So I'm going to make that happen. But in order to combine these 2 logs, they need to be on the same side of the equation. So I'm just going to subtract this one here from both sides. So I have log of x squared over 3, that's this one here, minus log of 8 equals 3. Okay, and now I can combine these 2 into a single logarithm, and remember, when you are subtracting logs, the resulting single logarithm is going to be the inside of this one divided by the inside of that one. So x squared over 3 divided by 8, you know, if you divide this fraction by 8, you basically wind up multiplying the denominator of the fraction by 8. So that's going to be x squared over 24 equals 3. Okay. Single logarithm, we are ready to exponentiate. We're going to exponentiate both sides by the base of the logarithm. Well, what's the base of the logarithm here? There's nothing written there. If you remember from yesterday, if you see a log with no subscript, like no base written at all, that means log base 10 of x. The 10 is implied. So this is actually log base 10 because there's nothing written there. So 10 is the base of the logarithm, so I'm going to exponentiate both sides of the equation by 10. So I have 10 to the log of x squared over 24 equals 10 to the third. And great. What's going to happen to this expression? Well, the same thing as before. Basically exponentiating by 10 and taking a logarithm base 10, they're inverse operations. They cancel out. The only thing that's going to be left is the inside of that logarithm, which is x squared over 24. All right, and all of that equals 10 to the third. That's 10, 100, 1,000. So that's 1,000, right? All right, so then this is now just a quadratic, easily solved. Multiply both sides by 24, so that's 24,000. And so x is going to be, looks like plus or minus, yeah, I'm going to, this is a little tricky. So for one thing, I suppose that you should simplify this root 24,000. Like, you can probably pull out some perfect squares. I don't really care about that right now. What I do care about is the fact that, you know, it seems like you have two different solutions here, positive and negative square root of 24,000. Technically, only the positive root is really a solution. Why? Because if you look at the original equation, you have log of x right here. If you replace that x with the negative root, negative root 24,000, you'll basically get an error. It's undefined. We haven't talked about this, but you can't take logarithms of negative numbers. It's not defined. So technically, the negative root is not a solution because, you know, if you plug it into the original equation, you don't get a true statement. The equation just breaks, right? So technically, it's just the positive root. But look, I don't want you to worry too much about that. That's like a super fiddly, small little thing. I'm not going to like really test you too much on that kind of thing. Just be aware that it exists. Okay, so that's the solution, you know, and that can be simplified, but whatever. The other thing I wanted to do, I told you I wanted to solve this equation in two different ways. If you remember at this stage, I was like, oh, you know, it's sort of nice to have just a single logarithm in the entire equation. And I was like, well, I can combine these two, but I have to move this one over to the left-hand side. And then I said, okay, so that's what I'll do. But I want to show you a different way of solving this equation. So I'm going to start over like from here and show you what it looks like. I'm just going to copy that step again. And I'm going to show you what it looks like if you don't combine everything into a single logarithm. So there's that step of the equation again. So let's say that I just exponentiate right now. Okay? Instead of bringing this over and condensing, say I exponentiate right now. So what do you get? You get, you know, 10 to the log of x squared over 3 equals 10 to the power of this, 10 raised to the entire right-hand side. Log of 8 plus 3, okay? The entire right-hand side became an exponent of 10. Now, the left-hand side here does simplify, okay? It's 10 raised to a logarithm, the exponentiation by 10 and the logarithm cancel out, and that just gives you x squared over 3. Great. What about this? Does the 10 and this log cancel? No, because of this plus 3. Let me just make the following argument. This expression here, 10 to the log of 8 plus 3, can be rewritten in the following way. You can rewrite this as 10 to the log of 8 times 10 to the third power. Okay? It's easy to see that these two expressions are the same if you go from here to here, right? It's like 10 to the blah times 10 to the other blah is 10 to the, well, you add the two exponents, right? So you can see that these two expressions are the same. Now here, you can do some great simplification. It's 10 to the power of log of 8. The exponentiation by 10 and the log base 10 do cancel. So this little guy right here, this thing in the box, does become just plain old 8. 8 times 10 to the third, okay? And then 10 to the third is, you know, 1,000, and you can solve the equation from here, and you'll get the same answer as before. But as you can see, like, this is kind of tricky. You know, a lot of people will do this, and, you know, they'll exponentiate both sides. A lot of people will say when they exponentiate by 10, they'll be like, oh, that's this. That's 10 to the log of 8 plus 10 to the third. No, that's not what it is, right? You have to, when you exponentiate both sides of the equation, the entire right-hand side has to become a single exponent of 10. You know, whatever this is, that's not a legitimate move, okay? Anyway, the first method is better, as I'm sure you can probably tell. So, yeah. Okay. Yeah, I think that's good for now.